Hello, Math 123 students. This is the 7A WWW assignment. So we're going to start off with 7A1, which is over the empirical rule. We're just going to do the very basics on this, mainly just knowing the three percentage spreads, what they actually mean, and we'll answer a basic question about that. You'll go into a lot more detail in class. So the empirical rule provides a quick estimate of the spread of data in a normal distribution. A normal distribution is what we have down here in this picture. It's a bell-shaped curve where we have this nice symmetry around the mean, okay? So given the mean and the standard deviation is a way that we measure the spreading out of our data from our mean. So from our center, from our halfway point, essentially for us, since when you have a normal distribution, your mean and your median are dead center in the middle of that graph, okay? So the standard deviation tells us how this data spreads out from the mean. Now, we can estimate that 99.7% of the data will lie within plus or minus 3 standard deviations from the mean. Okay, so that is the biggest spread down here, but let's talk about each individual one. So if you have your mean and you have your standard deviation, you can subtract 1 standard deviation and add 1 standard deviation to your mean. If you notice, we make these lines to mark. I took my mean on a number line, put it there, subtracted the standard deviation, got that new number, added the standard deviation, wrote down that new number, and between those two data values, I will have 68% of the area of my curve. So if you imagine shading in, so I'll kind of draw that for you. If you imagine shading in everything between these two bars, all the way, that is that 68%. So that's that first one, okay? Now, if you go 2 standard deviations below your mean, so that means you subtract the standard deviation twice and you add it twice, so we go 2 above it, that's going to be all of the area that you already included. So everything from, oh, it made a heart. Don't know why I did that. But it would be everything from here to here. I'm not going to highlight the whole thing, but imagine all of this area all the way up to the top of the curve being shaded in the pink now. That is going to be 95%. Okay, so 95% of your data is between whatever two values we get for those two marks. And then 99.7% of our data will be between 3 standard deviations below the mean all the way up to 3 standard deviations above the mean. And again, imagine me actually shading this in as a full complete curve, all blue, okay? So that is the 99.7%. Now we can get much more granular than this, and you will do that in class on, can we find the percentage between two of the marks? Yes. But right now we want to focus on just the main rule, which is the 68, 95, 99.7. So this rule right here, and it's detailed just like that, this part will be included on your formula sheet. So you don't have to memorize the percentages, you just have to know what they visually represent. And just as an FYI, the mean can be written as the mu, because that's the population mean, or it might be written as X bar sometimes for the sample mean. Sigma or S can both be used for standard deviation. Sigma is when it's the population standard deviation, so all of the data for the whole population. S is when it's for just a sample, okay? So let's look at our first example here. It says a set of exam scores is normal. So when they tell you that it's normal, that means we're dealing with the bell curve with a mean of 80. So I'm going to write that down here for my mean as a note for myself, and a standard deviation of 5, okay? So when you have a bell curve, the first step is to put that mean right in the middle as that mark on the x-axis. If you think about this being a number line, that's dead center, and half the data is above it, half the data is below it, okay? To get your other marks on each of these kind of lines, these are our standard deviation lines, we need to add and subtract that standard deviation. We add to go bigger, we subtract to go smaller. So we're just going to keep adding 5 to get our marks. So this would be 85, 90, and 95. If we subtract 5, this would be 75, 70, and 65. So now I have my spread of my data listed out on the number line, okay, based on my standard deviation and my mean. Now, the question says approximately what percentage of students scored between 75, so that is this mark, and 85, okay? So if we look at this, this is 1 standard deviation below my mean to 1 standard deviation above my mean. When you have that equal spread on each side, we went 1 below and 1 above, that is when you're one of the 3 big percentages. So remember, it was 68, 95, 99.7. So to go 1 below to 1 above, that is the 68%. Okay, so that's the first one. Now let's look at what they asked for the second question. So this one says between 65 and 95. So 65 is here, 95 is here. Just for context, I'll go ahead and highlight this to match what I did down there. But this one we are going 1, 2, 3 standard deviations below my mean, and 1, 2, 3 standard deviations above my mean. My mean is the 80. So we went 3 below to 3 above. Equal spread on each side. That's the final percentage. That was the 99.7%. Okay. And like I said, you're going to get a lot more detailed on the in-class notes with your teacher, but this is the using of the main rule. Okay. All right, then we look at 7A2, find and interpret z-scores, probability using a z-chart. So we're not going to do the z-chart on this part. We're just going to talk about the z-score formula. So that empirical rule that we just learned about, the 68, 95, 99.7 rule, sometimes it's called that instead of empirical, applies to data values that were exactly 1, 2, or 3 standard deviations above or below the mean. There could be times when the data value you are considering falls between those marks. In those instances, we will compute what is called the z-score, which is often abbreviated by the letter z. The z-score is the number of standard deviations, the value x, so a specific person's maybe test score, weight, whatever it is we're measuring, is above or below the mean, okay? So essentially what happens is you have lots of bell curves that you'll look at, and they end up having a similar pattern. We'll just be having our mean in the middle, and we'll have to add our standard deviation to go to the right, subtract our standard deviation to go to the left. We'll see many different varieties of numbers on this x-axis down here on our number line. The difference is this is going to have, a different picture for every change. If we get a new set of data and the mean changes and the standard deviation changes, we'll get different numbers on these bottom parts. Also, something else is, what if I wanted to know what's the percentage someone scored higher than maybe 87, which is somewhere between 85 and 90. We don't really know where that location exactly is. We can imagine where it is, but we won't have a way to reference it with a percentage yet. So that's what this z-score information helps us do. Essentially, we take raw scores and we're going to put them on what's called a standard normal curve. And that standard normal curve takes any data that we have. We take those raw scores and we take our mean and our standard deviation, and we use that information in that z-score formula to create a nice bell curve where the center or mean is always 0. 1 standard deviation above that will be the number 1. 2 standard deviations above it will be the number 2, and then a 3. Essentially, we're spacing it or condensing it, if our numbers are bigger than these, to this scaling, okay? And then we have the ones that are below the mean are going to be -1, -2, and -3. These are those marks for the actual standard deviations we normally would have gotten when we were adding or subtracting our standard deviations, like when we added the 5 and subtracted the 5 above. So the goal of this formula is to take all the raw scores, that mean of 80, that standard deviation of 5, and someone's maybe specific test score. Say someone scored an 87. And we want to take those and convert it to this scale so that this number we get for that person's individual score will tell us their exact position in reference to our mean of 0. Okay? That is the goal of what a z-score does. So this is the formula. You take the data value in question, so it's usually a specific individual, their weight, their height, their test score, whatever it is we're measuring. We subtract that from the mean of the entire data set, and then we divide that by the standard deviation of that entire data set, okay? So that in formula form is x minus the mean, which is mu, over the standard deviation, which is this sigma, okay? So if we look at an example here, it says the daily commute times in minutes for employees at a company are normally distributed with a mean of 35 and a standard deviation of 6. This is in minutes. Find the z-score for an employee whose commute is 26 minutes. Okay, so I wrote out everything I knew. The mean for all the employees is 35. Standard deviation for all employees is 6, so plus or minus 6 minutes. The employee in question had a commute of 26. So that specific person goes first. We always do the item in question, which is that one individual, minus the mean divided by the standard deviation. So 26 minus 35, all divided by 6. The top would be -9 divided by 6. This gives me -1.5. So if you imagine it, that means they are located right there on this bell curve, okay? That's where that person would be located. So we know they're below the mean, and you can actually write this. This means that the specific employee's commute time would have a position on the bell curve that is 1.5. Notice I didn't use the negative here because I'm going to describe that with the word below. So 1.5 standard deviations below the mean. Now, if they just ask you for the z-score, absolutely write it as -1.5. But if they ask you to interpret it, you can say just the value, and above would mean it was positive, below would mean it is negative. Okay, so let's look at this one. Now, here's the cool thing. Even though this is completely different data, that was commuting time, this is test scores, we're still going to be able to put this person on a bell curve that goes from -3 to 3. That's what the z-score allows us to do. And that allows us to then use those tables or charts that you're going to learn about in class. So scores on a statistics exam are normally distributed with a mean of 70 and a standard deviation of 8. A student scores 88. So this is the person in question. So remember, that goes first on top. We subtract the mean from that, so -70. We divide it by the standard deviation. So 88 minus 70, our top number is 18, divided by 8. And when you divide, sometimes you'll get decimals that go on for quite a ways. Look at your rounding directions in your homework and stuff, but typically z-scores are rounded to 2 decimal places if they go beyond that. This one luckily ends at the 2 decimal mark, so we'll just put 2.25. Again, always read your directions for rounding. So this is the z-score. So this person's position is actually above the mean, and it's probably 2 1/4, so somewhere around there. So 2.25. So notice we were able to then put this person into that standard normal curve. So we can see the exact position in reference to the mean, which is 0. All right, and that leads us to our very last section, 7A3, margin of errors and confidence intervals. Now, a lot of times people are taking surveys, and sometimes when you take a survey, you may not answer questions truthfully, you may not have read it correctly, they may not have sent the survey to everybody that needed to get it, or they didn't all return their surveys. So there's going to be errors within surveys. When people say, 45% of people agree with this statement because of our survey, that's not always a factual 100% that is true no matter what. There's going to be issues with any survey or any kind of polling that then makes their results kind of inaccurate. So with these problems, we will read the results provided from the survey and then apply a margin of error to the reported percentage to create a confidence interval. So a margin of error tells us within a certain percentage or amount of points, if we're doing a proportion, we are off we're either overestimating or underestimating that actual result, okay? So how you find your confidence interval is you add and subtract the margin of error from that reported percentage or proportion, whichever way they give it to you, and then we will write a sentence about the result. So here are some key terms. If they talk about sample size, that's just the number of people in the survey. A point estimate, we need that for our formula for the confidence interval, is a number calculated from a random sample that is used as an approximate value for the population parameter. If you're doing a proportion, so usually that'll be something like 4 out of 5 dentists agree, or 80 out of 100 people said yes to this part of the survey. So that P hat, that's what you call it with that little, it looks like a hat symbol above it, is the point estimate for your proportion. Sometimes your point estimate might be an average. They might say the average number of people or the average number of hours done is such and such, okay? If you have that, then we call that an average. So it's an X bar, and it's an estimate for our population mean, okay? So you're either going to have one of two things. You're either going to have, they're either going to give you the proportion or the average and you can just work with it, or you may have to find it yourself. Like if it's an average, you may have to add all the data up, divide by how many there are. If it's a proportion, they might tell you 80 out of 100, you'll turn that into a decimal so we can use the margin of error. So we'll look at some of those examples in just a minute, but we will either have this given to us exactly or we have to find it, and then they'll give us the margin of error as well. To get the confidence interval, the range of values that are calculated from a set of sample data that can be used to give the probability that the interval contains the true value of the parameter. What you do with that is you take your point estimate and you subtract the margin of error and you add the margin of error, and that makes our interval. So the margin of error is just the width of that confidence interval. It's a measure of that width. Okay, so let's look at an example here. So it says a survey of 1,248 IB Tech students shows that 78% of people will use quantitative reasoning after this class finishes. If the margin of error is plus or minus 3.2%, find the confidence interval and write a sentence about what this means. Okay, so that since this is in percentage and so is the margin of error, we don't need to do any kind of conversions. They've reported 78% will use it after the class finishes. But they said, oh, we could be wrong in either direction by 3.2%. So we take 78, subtract the 3.2 to get our lower boundary. That's 74.8. We take the 78, we add the 3.2 to get our upper boundary, which is 81.2. And then we can say our confidence interval is between 74.8% to 81.2%. Now, if we need to write that in interval form, which you will a lot for your homework, you write it, it looks like an ordered pair, but it's not. This is interval notation. Parentheses, 74.8, comma, 81.2, close parentheses. When it's written like this, it means every value between these two numbers is a possible true result instead of just saying it's 78%. We're saying it could be anywhere between, the true population result could be anywhere between 74.8 and 81.2, okay? Now, if they, and this again, I don't really love this because usually confidence intervals need to have a percentage of accuracy, but they don't do that in your homework. So they just say you are pretty confident that, and then we write our first one, so 74.8 to 81.2%. They've got the percent symbol there to say that these are both percentages of people will, and then we go back to what the context of the problem was. Use quantitative reasoning after this class finishes. Okay. So a lot of these, when you're working through them on the homework, you might be filling in just some of the blanks or choosing a drop-down menu to complete those parts if it is a sentence. Okay. Be very careful. You will need to pay attention to how the margin of error is presented, as that will help you determine whether or not you need to adjust any other values in this problem. Here's an example with proportions that need adjustments before creating the confidence interval. So I wanted to show you this one specifically because there's quite a few of these in the homework. So notice they gave me it's kind of like the 4 out of 5 dentist degree. They said, suppose we know that 40 out of 100 people polled preferred chocolate ice cream over vanilla. Construct a confidence interval for the proportion of polled people who prefer chocolate ice cream over vanilla, where your calculated margin of error is 0.075. So notice the margin of error is delivered to us in decimal form. So we should get our point estimate in decimal form as well. You usually want your margin of error and your point estimate to be in the same type of measuring system because that's how it makes sense to write the interval. So I'm going to start out with finding my p hat, because remember, proportion is a p, by taking and writing this fraction. It's 40 out of 100. And I'm going to go over to my calculator and just turn it into decimal form since my margin of error is in decimal form. So that would be 0.4. Okay. So now I'm going to do my margin of error to create my confidence interval. So we take our 0.4. And the first thing we do is subtract the margin of error from that. That gives me my lower boundary of my interval. And then I'm going to take my 0.4 again, because that's my point estimate. And I'm going to add the margin of error. Okay. So we'll take our calculator, subtract it first. So this gives me a lower boundary of 0.4. 0.325 and an upper boundary 0.4 plus 0.075 of 0.475. So 0.475. And there is my confidence interval for this information. All right, that is the end of this video. I hope you have a wonderful rest of your day.